Algebra 2 students, those of you who've missed the lessons due to various sport trips. Today, we're starting to talk about circular trigonometry. In other words, no longer are we talking about an angle inside of a triangle and how do we do things with sine, cosine, and tangent functions, but now we're going to start developing circular angles and how do we evaluate the 6 trig functions for angles around a circle. Well, the transition's not that bad, but this is an important slide here. So we already know right triangle trigonometry. In right triangle trigonometry, we have 2 acute angles. I pick one of them, and let's say I pick this one and call it angle theta. Well, relative to that angle theta, we would refer to this side as the opposite side, this side as the adjacent side, and this side as the hypotenuse. And so we say that the sine of an angle in a right triangle is O over H. The cosine of an angle in a right triangle is A over H. And the tangent of an angle is O over A inside a right triangle. And then, of course, we've got those 3 reciprocal functions that some of you are avoiding, but quickly you will not be able to avoid these 3 anymore. And just remember which is the reciprocal of which. So when we're doing right triangle trigonometry, we define the sine, cosine, and tangent functions and the 3 reciprocal functions in terms of the sides of a right triangle. Well, now, learning circular trigonometry, these definitions as opposite hypotenuse and adjacent hypotenuse and stuff like that just doesn't work because we're no longer talking about right triangles per se. So I want you to think of a circle overlapping the x, y coordinate system such that the center of the circle is at the origin of the coordinate plane. That is always the case when we're doing circular trigonometry. Now, in order to make an angle in a circle, you also have to have 2 rays. One ray is called the initial ray. The initial ray is fixed, it does not move, at the positive side of the x-axis. Okay, so I want you to imagine that one of the 2 rays that's going to make up an angle is always pointing on the positive side of the x-axis. That is where 0 degrees lives. Okay, now it takes 2 rays to make an angle. The next ray is a terminal ray. That is a movable ray that rotates around the circle. Now, for today, we only rotate the terminal ray counterclockwise. So imagine the terminal ray is currently lying on top of the initial ray, but then the terminal ray is movable. So let's say that the terminal ray starts to rotate in that direction. That's not the terminal ray, that's just me saying what direction. And then the terminal ray stops rotating and it hits a point on the circle. Let's say that that point is x comma y. Well, you see what's going on here. Let me move this 0 degrees out of the way. 0 degrees is right there on the positive side of the x-axis. This is an angle theta of rotation. In geometry, you would refer to this as an arc. So notice that that angle theta is not an angle in a triangle, in a right triangle in particular. So it wouldn't make sense to say that the sine of this angle theta is O over H. That's just not going to work because there's no triangle with an opposite side and a hypotenuse side. So what we have to do is we have to redefine the 6 trig functions. Well, let me show you how we're going to do this. Every angle theta in a circle is associated with a point xy on the circle and the radius of that circle. So you see the segment that goes from the center of the circle to the point xy is the radius of the circle. The ray that extends outside of the circle is irrelevant. It's just going on forever and ever. Okay, now I can redefine all 6 trig functions in terms of the point that the angle goes through on the circle and the length of the radius. But watch how silly this actually is. I'm about to draw something that's not really there. If I say that this is the point xy on the circle, well, when we were back in elementary and middle school learning to plot points, when we say that this point is xy, doesn't that mean we went over x units and then we went straight up y units? Now, I want you to remember, this right triangle that I just drew is not there. Hush, 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 it's not there. Well, do you remember from geometry that if I say that this arc is theta degrees, doesn't that mean that this central angle is also theta degrees? Central angle and arc are equal. Well, watch this. The sine of theta in a circle is not opposite over hypotenuse. That's triangle talk. But notice that if we go opposite this angle theta, we see y. And instead of this being called the hypotenuse, it's being called the radius. So in a circle, the sine of an angle is y over r, not o over h. The cosine of a circular angle is not adjacent over hypotenuse, it's x over radius. But notice secretly that's still adjacent over hypotenuse. You're just not allowed to call it adjacent and hypotenuse. The adjacent side is x and the hypotenuse is radius. The tangent of an angle theta used to be opposite over adjacent if we're being triangular, but here the opposite that's not really there is the y coordinate and the adjacent is the x. So we say that the tangent of an angle on a circle is its y coordinate divided by its x coordinate. Now don't forget, cosecant is merely the reciprocal of sine. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So we're going to say x over y. So now you have to put these away because we're not doing right triangle trigonometry anymore. We're setting up circular trigonometry. So I'm going to take my eraser and I'm going to fix this picture back up by erasing some stuff. So now we don't need to draw that triangle anymore. When I rotate around a circle theta degrees, I stop at a point xy and I have a radius. Well, notice that the radius is really just the Pythagorean theorem associated with the ordered pair. So x squared plus y squared equals radius squared. Well, can I say that the square root of x squared plus y squared equals the radius? And can I think about that as the formula that I need for finding the radius, and I don't even need to draw that triangle anymore? So let me show you how this is going to work. You'll see some problems like this on practices, quizzes, and tests, so be ready for this. An acute angle has its terminal ray passing through the point 3, 4. So let's draw a picture of this. X-axis, y-axis. Draw the point 3, 4. Okay, well, if I draw that segment, that's the radius of the circle, and then I'm horrible at this. Just imagine a circle. Ugh, terrible picture. But it doesn't matter. All I need to do is say r is equal to the square root of the x coordinate squared plus the y coordinate squared. That's r equals the square root of 25, which is 5. So I have determined that the radius is 5. Excuse me, I meant to write the number 5 there. So now I've got x, y, and r. So it says find the 6 trig ratios of that angle. The sine of that angle is equal to y coordinate divided by radius, 4/5. The cosine of that angle is x coordinate divided by radius, so that's 3/5. The tangent of that angle, this angle, theta, rotating around that far, is equal to y over x, so I guess that's 4/3. Cosecant is the reciprocal of sine, so cosecant is 5/4. Secant is the reciprocal of cosine, so 5/3. And cotangent is the reciprocal of tangent, so 3/4. So to practice memorizing your 6 new trig functions, you'll see problems like that. Now, I want you to read this next problem with me and set it up, but then I want you to press pause and try to work it out before you press play and check my answers. An acute angle has its terminal ray passing through the point 2, 4. So let's draw this picture. 2, 4. Okay. So there's the point 2, 4, and there's my best rendition of a circle going through that point 2, 4. So imagine that that angle theta is this arc, theta. How many degrees is that arc theta? We'll deal with that later. Now, r equals the square root of the x coordinate squared plus the y coordinate squared. So that's the square root of 20. Well, I want you to remember to go ahead and simplify square roots when they can be. So let's call the radius 2 square root of 5. Okay. So now, let's do our 6 trig functions. The sine of theta is the y-coordinate over the radius. But do you remember from past lessons and chapters, don't ever leave a square root in the denominator of a fraction. So you want to multiply the top and bottom by the square root of 5. So that would be 4 square root of 5 over 10. And then that would be 2 square root of 5 over 5. You'd want to say that's the sine of theta. The cosine of theta is the x-coordinate over the radius. Well, I could cancel those 2's. And then I can multiply the numerator and denominator by the square root of 5, and I'd get the square root of 5 over 5. The tangent of theta is the y-coordinate over the x-coordinate. Oh, I like that. So now, doesn't that say that the cotangent of theta is really easy? Just flip that. The reciprocal of 2 is 1/2. Okay, now, let's talk about the cosecant of theta. Cosecant is the reciprocal of sine. Well, you'd be really tempted to grab this answer and take its reciprocal. But that actually requires more work than what I'm about to show you. You remember this was the original answer for the sine of theta, 4 over 2 root 5? It's actually easier to flip that to root 5 over 4. And then, what's that? The 2 and the 4 cancel, the square root of 5 over 2. And then the secant of theta, don't flip this one, come back and flip this one, and you have 2 root 5 over 2, and the 2's cancel and you just have the square root of 5. Okay, so be aware of problems like that. It just helps you practice your 6 trig functions. Sine is y over r, cosine is x over r, etc., etc. You've got to memorize that. Now, I want to put away the circular trig for a minute. We just started it. And I want to go back to geometry class and talk about 2 special right triangles that Mr. Schaefer or whoever your geometry teacher may have been, if you weren't here, emphasized and stressed that it's really important to know about these. Do you recall that the 45, 45, 90 right triangle is called special? And when you had Mr. Schaefer, he probably drew a 45, 45, 90 right triangle, and he told you to just memorize, put a 1 on both of the legs because both of the legs have to be equal. The triangle is isosceles. And then the Pythagorean theorem says the square root of 2 goes there. But you see, that's not the only 45, 45, 90 right triangle. You could also have a 45, 45, 90 right triangle in which the hypotenuse is 2. Well, how could I change the square root of 2 to a 2? I could multiply by the square root of 2, and that would be a 2, right? So if I multiply everything else by the square root of 2, this would be square root of 2 and square root of 2. So that's another 45, 45, 90 right triangle. Well, what if a 45, 45, 90 right triangle had a hypotenuse of 4? Well, that would be doubling everything. So if I double everything, then that would be a 2 root 2 and a 2 root 2. You'll see what we're going to do with this in the next part of this lesson. Okay, what is the sine of 45 degrees? Well, if I use this triangle, opposite over hypotenuse would be 1 over the square root of 2, but I'd have to change that to the square root of 2 over 2. The cosine of 45 degrees is adjacent over hypotenuse, also 1 over the square root of 2, or the square root of 2 over 2. The tangent of 45 degrees is 1 over 1. Opposite over adjacent is 1 over 1. All right, well, the other 3 are just reciprocals, so the cosecant of 45 is the square root of 2 over 1. The secant of 45 is the square root of 2 over 1. And the tangent of 45 is, flip 1 over 1, you still have 1. So Mr. Schaefer probably emphasized you might actually want to memorize the sine, cosine, and tangent of 45 degrees. You'll see why in the next part of the lesson, and you'll see how I can be helpful with it. Now, the next special right triangle was the 30, 60, 90 right triangle. Mr. Schaefer probably drew a 30, 60, 90 right triangle, and he always put a 1 opposite the 30, a 2 on the hypotenuse, and a square root of 3 on that leg right there. Well, what if there was a bigger 30, 60, 90 right triangle with a radius of 4? Well, that would mean all I'm really doing is doubling everything on this triangle. So then this would be a 2 and this would be a 2 root 3. Those are 2 30, 60, 90 right triangles. But what do you notice? The sine of 30 degrees is opposite over hypotenuse. Or it could have been this 2 over this 4, but that's still a half. The cosine of 30 degrees is adjacent over hypotenuse, and the tangent of 30 degrees is opposite over adjacent, but we gotta multiply that and make it the square root of 3 over 3. I'll leave the other three, cosecant, secant, and cotangent, to you, but you might want to memorize these three. Well, what about the sine of 60 degrees? Well, opposite the 60 is the square root of 3 over the hypotenuse 2. The cosine of 60 is adjacent 1 over hypotenuse 2. And the tangent of 60 degrees is opposite square root of 3 over adjacent 1, square root of 3. You might want to memorize those. And yes, you're noticing something that I'll make a big deal out of in a later lesson. Notice that the sine of 30 and the cosine of 60 are equal, and the sine of 60 and the cosine of 30 are equal to one another. That is not a coincidence. There's a reason for that, and we'll discuss it over time. Now, after you work on memorizing these three sets of facts, sine, cosine, and tangent for 30, 45, and 60, let's take this right triangle trigonometry and let's apply it to circles. Okay, just bear with me. Notice in this picture I've got 4 concentric circles, one with a radius of 1, a radius of 2, a radius of 3, and a radius of 4. All of these circles are similar to one another, and I'm going to kind of prove it to you. So watch this. If I put a point at the center of each circle, if I go through the ordered pair 1, 1, 2, 2, oops, I messed up. No, I didn't. 2, 2. And then let's see, where is the point 3, 3? Right here. And here's the point 4, 4. If I draw a ray through those points, these arcs are all 45 degrees. Okay. So here we have a circle with a radius of 4 rotating around 45 degrees. Well, I wonder what that point is. Well, watch this. Right here, do you see that this was the 45, 45, 90 that had a hypotenuse of 4? Well, now instead of thinking that as a hypotenuse of 4, let's think of it as a radius of 4. So now 2 root 2 and 2 root 2. Well, here's what happens. This point is 2 square root of 2, comma 2 square root of 2. So when you rotate 45 degrees around a circle, you create an ordered pair where the x-coordinate and the y-coordinate are equal, and then you just have to figure out the radius. So now, let me erase a little bit of this picture. So now, suppose I come to this circle that has a radius of 2. Well, I wonder what this ordered pair is at the end point of the circle with a radius of 2 with 45 degrees of rotation. See, that's 45 degrees as well. Well, if this is the x-coordinate and y-coordinate when the radius is 4, then shouldn't this ordered pair with the radius of 2 be half of that? So this would be the square root of 2 and the square root of 2. So square root of 2 comma square root of 2 is the ordered pair on a circle with a radius of 2 that corresponds to 45 degrees. Okay. Now, suppose that I erase some of this and go back to the circle that has a radius of 1. Well, what is this point that corresponds to 45 degrees of rotation? Well, if this root 2 comma root 2 is the point on the circle with a radius of 2, then the circle with a radius of 1 the ordered pair would be divide the previous ordered pair by 2. So would this be the square root of 2 divided by 2? And let me put it up here. The square root of 2 divided by 2, comma, the square root of 2 divided by 2 would be this point right here. Okay. So just try to remember that for another slide or so, is that right here, when I go 45 degrees on a radius of 1, I get the square root of 2 over 2, comma, the square root of 2 over 2. Well, that's a pretty significant ordered pair you'll see in just a few minutes. Now, let me do this one more time, and we'll probably reach a good end for this lesson right here. Suppose that I draw a 30-degree angle around the circle. Okay, well, let's see. I'm going to go back up to my 30, 60, 90, and I want to kind of show you something. Notice that this hypotenuse of 2 has an opposite 30 of 1. So watch what I'm going to do. If I go to the circle with a radius of 2, and I notice that the y-coordinate is 1, well, then if I come out here to this circle with a radius of 2, well, let's see, where does that circle with a radius of 2 correspond to a y-coordinate of 1? Is right there. So if I draw this, I'm almost certain that this is a 30-degree angle, this is a 30-degree angle, this is 30 degrees, and this is 30 degrees. So if you'll indulge me for a few more minutes, I'm going to do kind of the same thing. So let's talk about a circle with a radius of 4 corresponding to 30 degrees. So right here, we're going all the way out to the big circle with a radius of 4. Well, if we scroll back up a slide, do you see this hypotenuse of 4 has a 2 root 2, nope, it's the wrong one. This one has a hypotenuse of 4 over here, has a 2 root 3 and a 2. So then that translates to this ordered pair being 2 root 3, comma 2. But what if I back up to the circle with a radius of 2? What is this ordered pair when the radius is 2? Well, would that be half of the previous one, square root of 3, comma 1? So when a circle goes with a radius of 2 goes to 30 degrees, it stops at the ordered pair, square root of 3, comma 1. But here's the fun one. If I erase and go back to a circle with a radius of 1, here's a little bitty 30-degree angle of rotation. What's this ordered pair? It's half of the radius of 2. So would that be the square root of 3 over 2, comma 1/2? Here's what I'm trying to show you. It seems like the circle with a radius of 1 is extremely, extremely nice. So imagine that what I'm doing here is I'm zooming in on this circle with a radius of 1. Okay, well, let's see. If I zoom in on that circle with a radius of 1, well, what did I just discover? If I draw a radius of 1 to the point that corresponds to 30 degrees, my ordered pair was the square root of 3 over 2, comma 1/2. If I drew my circle with a radius of 1 to the point that corresponded to 45 degrees, my ordered pair was the square root of 2 over 2, comma the square root of 2 over 2. And if I rotated my terminal ray to 60 degrees, my ordered pair would be 1/2, comma square root of 3 over 2. What is the significance of these three ordered pairs for 30 degrees, 45 degrees, and 60 degrees? Well, have you memorized that the sine of 30 degrees is a half, and the sine of 45 degrees is the square root of 2 over 2, and the sine of 60 degrees is the square root of 3 over 2? Well, what do you notice when you look at those ordered pairs? Are you noticing that the y-coordinate is the sine of 30, this y-coordinate is the sine of 45, and this y-coordinate is the sine of 60? The sine of 45 degrees is, oops, sorry, I've already done that one. What about the cosine of 30 degrees? Well, it seems I've memorized it as the square root of 3 over 2. The cosine of 45 degrees, I've memorized it as the square root of 2 over 2. And the cosine of 60 degrees is a half. Well, are you noticing that this is the cosine of 30, this is the cosine of 45, and this is the cosine of 60? It turns out that when you consider the unit circle is the circle with a radius of 1, every ordered pair around the unit circle is the cosine of that angle is the x-coordinate, and the sine of that angle is the y-coordinate, because y over r becomes y over 1 if the radius is 1. So in the unit circle, we can say that the sine of the angle is just the y-coordinate, as long as the radius is 1. X over r, which is cosine, becomes x over 1, or just x. So in other words, as long as the radius is 1, the cosine of that angle is the x-coordinate of the point there. So you're going to be working very hard at memorizing these three ordered pairs. I'm going to end this video here and have another short one for you in just a few minutes.